my name is Sinchana Hegde, and I'm a final year mechanical engineering student at NIDK Suratkal. My non-technical hobbies include theatre and dance, and from the technical point of view, my areas of interest are robotics, artificial intelligence, computer vision, image processing, and machine learning. I got into it because I was very interested in things like path planning, and it seemed very logical and very fun when I started off. And as I eventually started going into it more and more, I was more interested and discovered that it is where my passion lies. So here I am trying to discover more along that path. So today I'll be giving you an introduction to robotic path planning. What is robotics? Robotics is an interdisciplinary research area that falls right at the interface of computer science and core engineering. It involves design, construction, and operation of robots. What is path planning? Path planning, which is also known as motion planning, is a computational problem to find a sequence of valid configuration that moves the object from the source to the destination. The goal is to develop techniques that would allow a robot to automatically decide how to move from position A to position B, which in our case, the object is a robot. What are the different path planning algorithms? The first three basic algorithms that you'll come across if you delve into path planning is Grassfire, Dijkstra, and A-star. So in this grid, you can see that there are some black squares and some white squares. And the black ones are the obstacles that the robot cannot traverse. And the white ones can be thought of as nodes, which can act as steps or as a path for the robot to move along. And the green node is the start node, and the red node is the end node. So we can think of this in the form of nodes, and each node being connected via an edge. So it's kind of like a graph. A graph consists of a set of vertices V and a set of edges E that link pairs of vertices. And in this grid graph, we will implicitly associate a cost or distance of 1 with every edge in the graph, since they link adjacent cells. The goal is to construct a path through the graph from the start to the end. Typically, there are many possible paths between two nodes, and we are usually interested in the shortest path. We will discuss three algorithms which can achieve this goal, starting with Grassfire. So what is Grassfire algorithm? As you can see in the first image, what we do is we start off with the ending node with a value of 0. On every iteration, we find all the unmarked nodes adjacent to the marked nodes and mark that with a distance value of +1. So in the first one, you can see the 4 squares surrounding the 0th node is marked as 1, and the nodes that are adjacent to the ones that are marked with 1 are marked with 1 + 1, that's 2, and the next one is marked 3, and so on. And when we proceed this way, we see it's marked all the way till 9, with the starting node being 10. So now you can guess why it's called Grassfire, because on every iteration, the marking radiates outward from the destination like a fire spreading, and hence the name. To move towards the destination from any node, simply move towards the neighbor with the smallest distance value. So in this case, it starts off with 10 and moves to 9, and then it moves to 8 and 7, 6, 5, so on till 0. The next algorithm is Dijkstra's algorithm, which is easily the most popular algorithm for path planning that there is out there. So what happens in Dijkstra's algorithm is we consider a slightly different kind of grid, because Dijkstra also works with cost or distance that is not implicitly or explicitly 1. We can give different distances and different costs to each of the edge. So here that we can see A, B, C, D are the vertices, and the red lines are the edges, and each of them come with a value that's marked right above the edge. So we start off with A0, and what we do here is write the number equal to the shortest distance to get that node next to the node name. So from A0 to get to B, it costs 1. So we write that here. We write B, 1. And from A to D, it costs 2. So here we write D, 2. And A to F, it costs 5. So we write F, 5. Now to get to C, there are multiple paths. Either we can go from A to B to C, or A to D to C, or A to F to G to E to C. There are multiple possibilities. So first we're going to check from B, the first path possible. A to B to C is B has a value of 1, and the distance from B to C is 7. So we're going to write 8 next to C. But if we try the other path, that is from A to D to C, D has a value of 2 and the path from D to C has a value of 3. So now C is going to have a value of 5, which is less than 8. So we replace the value of C to 5 from 8. So now we know that the shortest path has to be A to D to C. So we store the parent of C as D and the parent of D as A. So we keep going this way to find that the value of G should be 10 and that the value of E should be 6. So our final path will be A to D to C to E. So this is how Dijkstra's algorithm works. And since it can also incorporate the cost or distance of edges, it is considered to be better than Grassfire. Our third algorithm is A star, which is the most important algorithm in path planning. When applied on a grid graph where all of the edges have the same length, Dijkstra's algorithm and Grassfire algorithm have similar behavior. They both explore nodes in order based on their distance from the starting node until they encounter the goal. A-star search attempts to improve upon this by incorporating something called a heuristic function that guides the path planner. What A-star algorithm does is that at each step, it picks the node according to a value f, which is a parameter equal to the sum of two other parameters, g and h. G can be considered as the movement cost to move from the starting point to a given node on the grid, and h is the estimated movement cost to move from that given node on the grid to the final destination. This is often referred to as heuristic, the value h, which is nothing but kind of a smart guess. We really don't know the actual distance until we find the path, because all sorts of things can be in the way. There are many ways to calculate this heuristic function h, but the two most popular methods used are these two, Euclidean distance and Manhattan distance. As you can see, it's given by the general diagonal formula, and xn, yn is the node you are currently in, and xg, yg is the goal node. So basically what happens is g is the distance of the node from the starting node and h is the distance from the end node. In this, A and B are the start and end node respectively, and what is denoted in the top left corner of each green box is the value g, and what's on the right side is the value h. So as you can see, the number in the center is the sum of g and h, which we will call f. So from A, looking at all the surrounding nodes, we see that 42 is the least or the shortest distance. So we move diagonally to 42. And 42 again has surrounding green cells, out of which it remains the same in the diagonally forward node, which makes sense logically if you think about it, that the diagonal must be the shortest distance. So it's going to move again to that. So if you look at this second image, you see that from A to B, the shortest distance was along the diagonal, and the f value never changed because there were no obstacles, or the distance was not changing from one node to the next node along that path. And you can also observe that the g value is increasing as you go closer to the destination because you're moving away from A or moving away from the source node, and h value is decreasing up to 0 as you reach the destination because the estimated distance to the final destination reduces as you move. Now let's introduce an obstacle, and we see that for A, the values still remain the same. So we can move to 42, it being the least node. And now 42 has 48 in 3 directions. So what do we do next? Also, you can observe that over here, 48 and 62 were the only 2 nodes that had a possibility of moving diagonally forward. So those 2 are the only 2 values that remained the same. The rest of them changed. So now from 42, we'll explore all 3 directions, this 48, this 48, and this 48. And we see that this gives 54, this gives 62, 54 being the lesser one. We will try to traverse in that direction, but also go in this direction in case it becomes lesser in the future. And here you can see that the least value was 68 in the end, because from 48 we got 54, from this 48 we got 62, and from this 54 we got 68, and from this 62 we got 68, but then that 68 remained constant as we moved directly in the least possible adjacent cell, and we didn't have to go all around like in this case. So in A star, we see that we get the shortest path without having to travel all the cells in the map, because there were so many nodes that we did not have to cover, which we would have to in case of Dijkstra's and Grassfire. This is why A star is considered the more efficient algorithm and the most important algorithm, because the procedure is similar to the previous algorithms, except here you can calculate G, H, and F and not traverse all the nodes to find the next step. More about this can be found out on Coursera through the robotics course by University of Pennsylvania.
Thanks for watching. Subscribe and click on the bell button as to not miss out any content. Contact us here.